All right, so the first talk of this session is Francis, whom we all know, and he will tell us the surprising result that if you do exclusively worst-case analyses, it doesn't actually tell you everything there is to know about stochastic gradient methods. Weird. It's very surprising. Shocking.
All right, so I will try to live up to the expectation now. So, all right, so before I start, I'd like to thank the organizers for inviting me. It's a pleasure to be in Cambridge, and compared to last time, it's sunny and warm. And this was like Richard Samworth did impose that, and he managed to deliver. So this is joint work with my PhD student Lucas Pio Vivien and his co-advisor Alessandro Rodi. So the 2-minute summary is as follows. So we're going to consider stochastic gradient in the context of large-scale machine learning or statistics, and the idea that those algorithms will process observations one by correcting errors as you see more and more data. And as mentioned by John, there is like two opposite sides of the story. You have the theory side, and this has been known for the last like almost 30 years. A single pass is enough. So what I mean a single pass is I have n observations, and I take the first one. I update my parameter to the second, third, up to n, and then I stop. So this is a single pass, and this is known to be optimal in many aspects, and I will make this precise later on. But now if you go to practice, everybody does multiple passes. So after you see the nth data point, you start again from the first one, go to the entire data set, and start again. Okay, so there's a big discrepancy between theory and practice, and when I say it works better, this could be like really better. Typically, single pass SGD may tend to underfit. And the goal of today is to have those two match. And there will be, so this is the goal of today. And so I'm going to, of course, this is still true, okay? So, but this will be only for a set of problems that we call easy, okay? And then for those, the non-easy problems, which I will call hard, then you do need some multiple passes. And as a bonus, we can quantify the number of passes that you need, and the somewhat surprising result is that you may need a number of passes that grows with the number of data points, and all that to get the best performance, of course. And so what is going to be interesting from my point of view is the fact that we're going to use tools from kernel methods, so from like reproducing Hilbert space theory, but which can be used either in the classical non-parametric setup. I want to do non-linear estimation, but those tools, those conditions do apply in a large D setup. So to me, when you work on, even if you do least squares in dimension D, when D is 1 million, it's like D is infinite. Okay, so the tools that you need are essentially the tools that are from infinite dimensional problems. All right, so this is the goal of today. So let's start. So first, of course, this is going to be like limited in scope. We are not proving that for all problems you should do multiple passes. We do this for a very subset of problems. This is least squares regression. So we have some data xi, yi. So xi can be an image, yi can be a label on that image, and we assume they come IID from a given distribution. We have n observations, and we do linear predictions, which are linear in the parameter theta, which here I first take in RD. So I have a feature vector phi of x. So this is assumed to be given at this time. And I'm doing linear predictions in that vector phi of x. And I'm going to consider least squares. So I'm going to consider theta star the optimal linear predictor in my class. And the reason why I'm considering like finite dimensional vector spaces is that theta star always exists in your vector space. Okay, so when I will go later to infinite dimensional spaces, this is not necessarily true that the optimal function belongs in your Hilbert space, but in finite D this is true. And the goal, and we're going to make some assumptions throughout the talk, very basic ones, that the features are bounded in the Euclidean norm, that my labels are bounded, and that my residual on top of my linear prediction is bounded. So in terms of algorithms, we assume we know the bound of the features, okay, so, but we don't need to know the bound M or the bound sigma. Those are just here to get bounds, but we don't need them to run the algorithm. So we're going to consider performance of estimators. So this is going to be done in terms of predictions. So F is the error on unseen data, and theta hat will be my estimator based on my sample. So this is random because the data are random, and I'm considering the excess risk with respect to the optimal prediction function. So this is always non-negative, and 0 if I have the optimal prediction. And it's well known that the best you can do is sigma squared d over n, and this is obtained by the simplest algorithm, ordinary least squares. We obtain that. Okay, so this is the usual least square setup. But the question is, what if n is more than d? Okay, so I'm going to show examples when you do analysis of text data, when you represent the text using a bag of word assumption. So d is the size of your vocabulary, and this can be thousands or millions, and often n is more than d, and we still apply techniques, those techniques when n is more than d. Okay, so we need to add some assumptions to really, if you want to show that our techniques can be applied also to high-dimensional data. This talk is orthogonal to sparsity, so I'm only assuming least square square L2 regularizers. So for that, we need to make some assumptions on the covariance matrix. So I'm not going to center the data. So this is a second order moment, and on theta star. So what are those assumptions, which are so classical in statistics? So first is the covariance matrix. So I'm going to call lambda m of sigma the eigenvalues of the covariance matrix in decreasing order. And this is one plot of the eigenvalues for some used data set. So text data when d is quite large and n is large but still quite smaller than d, and so the eigenvalues decrease. Okay, so in a log plot they decrease more or less like a line. So you have data will typically exhibit decay of eigenvalues, and so going to consider decays of the form 1 over m to the alpha. Okay, when m is the number of the eigenvalues. And it turned out that assuming this is almost equivalent to assuming that the sum of the power 1 over alpha of those eigenvalues is small. So here when I say small, that's small compared to n. So when I'm in finite dimensional setup, all quantities exist. So I have to say they're always finite, but I have to say they're finite, they're small compared to n. When I go infinite dimensional, that will mean they're finite. Okay? And so it's small compared to n, and so this will be the essential assumption for the covariance matrix. We're going to assume that for the eigenvalues decay as 1 over m alpha. So alpha is typically more than 1, okay, because my sigma has a finite trace. Then from the theta star point of view, so theta star is my optimal linear predictor, and you want to characterize the complexity of the prediction based on the norm on theta star. And what we're going to use, again, this is following usual quantities in kernel methods, is not only the norm of theta star, but the norm rescaled by the covariance matrix. And here I'm using a scaling of 1/2 minus r for reasons which I don't want to go over. And what you can see immediately is that if r is 1/2, okay, then you get the norm of theta star, and this is often the usual way of characterizing the complexity of my optimal predictor by the norm of theta star. And as you get, since the eigenvalues of sigma are typically going to 0, the larger the r, the simpler the problem, and the smaller the r, the weaker the assumption, and typically the harder the problem. So in particular, r equals 0 is always true because sigma 1/2 theta star, the norm of that is essentially the norm of my optimal predictions, the L2 norm, and this is finite. Okay, so we have R will decide if my problem is easy or hard. So what is known from existing work is that indeed the value of R will tell you if you're easy or hard, and the value of R depends on the value of alpha. Okay, so you can describe with easy problems where R is big, and R 1/2 is not being easy or hard. So often we look at papers, they often say, if I'm well specified, my theta star is in my set, then I'm easy. This is not the correct boundary. The boundary is more alpha minus 1 over 2 alpha, because most algorithms which work for R being 1/2 also work for R all over that blue region. And so, and the hard problems will be the ones for which R is less than that. So why do I say, why do I separate easy from hard like that? Because for the easy problems, it's known that every algorithm will achieve the optimal rate of estimation. So for those problems, it's known that the optimal rate of estimation, so the excess risk over the optimal predictor, goes down to 0 at a certain power. So the expert in the room will recognize the power. The non-expert do not need to look at the details of that rate, but this is the optimal rate. And as I mentioned, this is obtained by any algorithm which is reasonable. So regularized ERM, okay, early stop, gradient descent on the expected risk, on the empirical risk, and also single pass SGD also achieves it. Okay, so this is by easy problems. Okay, so maybe the confusing aspect is that easy or hard is not related to the power over there. Okay, so it's related to the easiness for simple algorithms. Do simple algorithms achieve the optimal rate of convergence? And for hard problems, the one where R is smaller, so where the function which you want to learn is less smooth, then we know lower bound, which is of the same form, but it's not known, okay, as far as I know, that this is optimal or not. Okay, the best known upper bound is this, and you can check that this is bigger than that. Okay, it's not clear what is the exact optimal rate in that situation. So the talk will mostly focus on that. Okay, and show that on those problems we can do better by doing multiple passes. All right, so what will be the algorithm? So we're going to consider stochastic gradient. So let's review what I mean by stochastic gradient. So this is my expected risk, okay, the square loss. In that context, SGD is often referred to as the least mean square algorithm. And this is the iteration. At step I, I'm computing the dot product between my feature and my current estimate. Take the label, take the residual, and do a step, multiply steps toward the feature vector times the residual. This is just SGD. So what we have showed with my colleague Eric Moulin a few years ago is that if you take a constant step size, okay, so this is somewhat deviating from the usual setting where the step size goes down to 0 as you get more iteration. So if you take a constant step size that depends on the norm of your phi of x, then you get convergence of the average SGD algorithm. So here, what I mean by averaged is that at the end of the, when I do a single pass, at the end, I take the average of all of my estimators, and this is called theta bar n over there. So after I do that averaging, the excess risk goes down to 0 as a quantity that depends on various quantities. So the noise in the problem, so we reobtain the sigma squared d over n, which we know is optimal. And since we do optimization, we start from some theta 0, and we forget it at a rate which is here again 1 over n, and we have later work showing that this term can be brought down to less than 1 over n if you want to, and recover the sigma squared d over n. All right, so this is the algorithm. So to give you a bit more intuition on how it works. So again, this is the LMS recursion that we have. And so like all stochastic gradient, they iterate from a Markov chain. Okay, so this is true because we have essentially independent data. But because gamma is constant, that Markov chain is homogeneous. The dynamics does not change with iterations. It would change if the step size gamma was going down to 0. But it's constant, so you're homogeneous. So you can, if you add a few assumptions, this is going to converge to a stationary distribution pi of gamma. So essentially, this algorithm does not converge anywhere. So you start from theta 0, you forget where you start, and you end up oscillating and around a quantity which I call theta bar of gamma, which is the expected value of theta under the stationary distribution. Okay, so it's not converging. Okay, but the beauty with least squares, because the gradient is a linear function, average gradient means that the gradient of the average is 0. So in fact, we oscillate around the true value. Okay, so this is the true value which we care about. So now we are back in familiar mode, is that we have a Markov chain which is converging to a stationary distribution. Hence, if you do averaging along the path of the Markov chain, like I'm doing, you should converge to the expected value under the stationary. And there's multiple versions of those ergodic theorems telling you that you converge with a distance rate 1 over root n. And since we measure performance with square distances, we take the square of 1 over root n and we get 1 over n. So the fact that we do converge as 1 over n is almost a consequence of the constant step size setup. What is not obvious is what you have in front. Okay, the constants are a bit more complicated, but so if you want to know more, you can look at the paper with Eric. All right, so this is like the main story. So simple example in small dimension. So in all of my plots, I will always show a number of observations. So because I'm doing single pass SGD here, this is number of iterations as well. And on the y-axis, distance to optimum in logarithmic scale. And so before averaging, this is in dotted, and after averaging, this is in plane. Various values of the step size, constant, and a decaying step size. And what you see that before averaging, it's not converging, it is oscillating. And as soon as you do averaging, you get you converge to a nice line which is of slope -1, highlighting the fact that we get a 1 over n convergence. Okay, I'm just showing this to highlight the fact that the constant step size, which is crucial here, does not converge before averaging. Bigger data, okay, so let's take only the right plot. This is the news data. It's predicting if news articles are speaking about, I forgot what, but probably sports or finance. And so again, number of iterations, performance in logarithmic scale, and again you see that the constant step size does outperform the decaying step size. So here, first example of multiple passes. Here in the slide here, I'm generating my data myself, so I have access to infinite amount of data, and I can compute the test error exactly because I know the distribution. In practice, when I take data, I have to have a finite amount of data to learn from. I keep some for evaluating the performance, but I have to do multiple passes, okay? Because I may do a single pass, but in fact, in this plot, the black line over there corresponds to a single pass. So after I do a single pass, okay, I get a reasonable like excess risk, but if I keep on doing it, I do better, okay? And this is in log scale, so when I go from there to there, it's like almost 100 passes. When I get there, it's like 10 passes of the data. I do much better than a single pass. Okay, so the goal of today is to provide one explanation of that behavior. All right, so for that, now I have to link the two first parts of the talk, which were first on least squares, assumptions on the problem, like covariance matrix plus theta star, to this SGD thing, and this is what we did with Unriria. So if you assume now, take SGD and try to put assumptions on the covariance matrix of theta star, what can we say? So exact same plot as before. So your data will have a decay of eigenvalues. Can it be used by the algorithm? And so what we showed with Unriria is that the sigma squared d over n could be replaced by a quantity that will depend on the decay of eigenvalues. So you can check when alpha here is infinite, I guess 1 over alpha is 0, sigma power 0 is identity, trace of identity is d, and I recover sigma squared d over n. So that bound does include the other one. But when alpha is anywhere else, then d is replaced by that trait, which is a dimension-free quantity, but I pay in terms of rates. Okay, I'm not going to get 1 over n exactly. I'm going to pay in the rate a bit, like I have an extra power 1 over alpha, but I gain by having this trace of sigma of 1 over alpha instead of the dimension. And on the right, what I'm plotting the red thing over there, okay, as a function of alpha. Okay, we will show that when alpha is infinite, we know it's equal to d, and D here is 10,000. So we know that this is going to be very large. But as you vary alpha, as you change assumptions, then this can go to something which is like much smaller. So in a sense, when you do like stochastic gradient, you have adaptivity to the decay of eigenvalues. You don't need to say in advance if I'm going to be a decay as m minus 2 or m minus 3. This will adapt to the problem. So this is on the covariance side. You can replace sigma squared over n by something which is will be much smaller. Similarly, for the optimal predictor, almost all of optimization is considering as a criterion how far I am when I start from the optimum using the square norm. Okay, so this is very classical, but in many setups this may be either quite large or even sometimes infinite, whereas if you use a finer quantity, okay, depending on the covariance matrix, then we can get a better bound. And as I mentioned already, R equal to 0 is always satisfied. So this is never a totally vacuous assumption. And if you assume that assumption, that this is small, then you can replace this 1 over gamma n, which we had before with Eric, by something which is a bit finer, and we may lose in the power of n, okay, but at the expense of replacing that potentially large quantity by something which is finite. So remember that when I'm going to consider Hilbert spaces, this will be infinite if my model is misspecified, but this may be finite. Okay, so this is the key here, is to replace quantities, this one and this one, which may be very large, by something which can be much smaller for finite n. So we lose in the power of n, but we gain overall. All right. So now we get the adaptivity result of SGD, that what I've described above is true for all alpha and all r. So I can take the infimum, okay, of the alpha, and SGD has some form of adaptivity to those quantities. And so now, once you see this, you may want to optimize the step size, because when the step size is big, the noise of the problem will be hurting you. Whereas if gamma is big, you will tend to forget initial conditions earlier. Okay, so here what I've done is that maybe I should have said it. I'm starting from 0. So when I'm starting here, so I had like the distance from initial conditions to last point, but since I'm starting from 0, I can replace theta 0 minus theta star by theta star, and this is what I'm going to show from now on. I start SGD from 0, which is by the default initializer anyway. All right, so now if you optimize for the base gamma, okay, which will be now depend on n, then you can show that I recover the rate which I had from before, the n power minus 2r alpha over 2r alpha plus 1. Then this I get optimum. Okay, so this is just like summarizing the current results. So now let me look a bit at kernels. Okay, so how do I do it with kernels? Because I want to do also non-parametric estimation. So if phi of x is in the Hilbert space, if I look at my recursion over there, I will not try to implement this in a Hilbert space in my computer, but I realize, people have realized, okay, not us, that theta I, if you start from 0, will be a linear combination of the phi of xi. This is a real number, so at the end, theta I is a combination of the observations. So I can, instead of storing theta I, I store the linear the coefficients, and I can update the coefficients easily by that formula, by just putting that back into the equation. And what I see is that everything will depend not on the phi of x, but on the dot product between phi of x and another phi of x, which is called the kernel. So as long as I know the kernel phi of x dot product is something phi at a different point, I can run the algorithm. This is the whole story of reproducing kernel Hilbert spaces. And so in terms of running time, I've moved from O of nd, which was the complexity in dimension d, to O of n squared, because every step here is O of I. So the I step is O of I, so overall is n squared at the end. So to make things concrete, let's look at the Sobolev spaces. So I have x is 0, 1. Okay. What we do applies more generally, but just to make things concrete. So take 0, 1, begin to represent functions through the Fourier series, and this corresponds to living in a small L2, and having phi of x will be a cosine plus a sine, but I don't have space for the sine, and it's a weighted Fourier basis by lambda m, exactly the eigenvalues of the covariance matrix. This is made for that. Okay, so I'm using like x is 0, 1 and uniform distributions, so that the lambda m here is exactly the eigenvalues of the covariance matrix. The kernel can be computed at this like infinite sum, and for some values of lambda n, there is like an exact formula based on Bernoulli polynomials. And if you do something like that, then if you take this lambda m being the decay which I have described, you get a Sobolev penalty. So if you consider now the functions defined from theta, then the norm of that function is defined as the norm of theta, and this is the norm. So it will depend on the Fourier coefficients of your function over lambda m. This is by definition of the Hilbert space norm. And what you get is that you get exactly the L2 norm of a derivative of f. Okay, so if I take alpha equals 2, okay, then I get like the first Sobolev space in 1D. Okay, this can be generalized, but essentially when I'm making assumptions on a strong decay of the eigenvalues, I'm essentially assuming like a Sobolev penalty with higher order. Now what becomes interesting is that I can choose, if I look at my adapted norm, okay, which depends on my covariance, now it's covariance operator because I have infinite dimensions, then I can do the exact same thing. So I get here lambda m minus 2r, and I'm replacing that derivative as something which is potentially higher or lower. Okay, so this is what I obtain. So in particular, when r is 1/2 the match, but when r is smaller, then I am assuming something which is less than differentiable. So in particular, if my theta star may not be in my Sobolev space, I may have like a weak function which is not differentiable, and then this will be infinite, but those ones could be finite. Because the whole goal here is to have potentially theta which is less smooth than your Hilbert space. It's less smooth than what your Hilbert space is saying. All right, so now to get to the multipass results, there is a price to pay. Okay, for the moment I was just reviewing existing work, and the price to pay is one extra assumption. Okay, so this is an assumption which was used by Ingo, Steinbart, and co-authors, which tells you that your feature vector, phi of x, is bounded, but also bounded related to the covariance matrix. So we know that when mu here is 1, this term disappears, and then we get the norm of phi of x. So we know that when mu is 1, my assumption is known and not super strong, but I need this to be true for mu less than 1, and you can check that for Sobolev spaces, mu is 1/alpha. Okay, so we are for those spaces we get something which is tighter. So for the experts in like non-parametric estimation, then you can show that this assumption is essentially equivalent to have a bound between the L infinity norm and the L2 and the Hilbert norm. Okay, so it's known that the L infinity norm is bounded by the Hilbert norm. Okay, so when mu is 1, this is known, but we need a bit more. We need to be able to squeeze out of the a bit of the L2 norm, and this is something that like Ingo Steinbart has used, and which we are using as well. So for the expert in the room, you can also show that this implies like bounded leverage scores. So this is mysterious, but this is you can talk to me after the talk if you want to know more about that. All right, so now let's go to the new results. So we have what do I mean by multipass SGD? So this is one version of multipass SGD. So this is sampling with replacement. So I'm assuming I have like n observations, okay, which I know, and at every time step u, I'm going to select an index I of u here uniformly at random between 1 and n, and take a gradient with respect to that to the pair xiu and a yiu. Okay, so this is a sampling with replacement, and I'm going to call theta t the average iterate after t iterations, and I'm assuming I'm making more than a single pass. All right, so this is a new result that we have. So we're going to assume that we have a hard problem. Okay, it should be less than. Excuse me. So this is a mistake. Then, depending on the value of mu, okay, then we propose a number of iterations. Okay, and given that number of iterations, we achieve, after doing multiple passes, okay, we achieve some rate of convergence. We have two setups when mu is small and when mu is large, and again mu smaller means making stronger assumption. And yeah, so it's a type of results. And before I describe what it means, so let me just mention the proof technique is taken from Rosasco and Villa, and the proof technique is essentially based on comparing the SGD recursion to the full gradient descent on the empirical risk. Okay, so you show that that's the question. You show that gradient descent and SGD, they stay close together. If you do gradient descent on the empirical risk, it will end up converging to the ERM, which is overfitting. So the performance of totally minimizing the empirical risk will not be very good. So if you consider number of iterations, T, this is performance. And if you consider the performance of gradient descent on empirical risk, it will start to go down, and then it will start to overfit because you end up minimizing the empirical risk. And what we show is that SGD will follow this quite closely, in fact. Okay, and the benefit is that it's going to follow it, but by doing SGD, which is like n times faster, and hence we stop essentially there. And that thing is to tell you that this is where we stop. Yeah, John?
T is theta of n to the alpha over 2r plus 1?
You mean like, is the power incorrect?
It looks like a negative power.
Yes. No, it's like, no, we are super good, we do like, no. Yeah, sorry, no, of course, no,
It should just be plus alpha.
It's surely a plus, but the idea is that that constant is supposed to be bigger than 1. Okay, you do more than a single pass, and I'll check. Okay, yeah, so this probably also a mistake in the paper, but that's fine. Mistake, no, a typo in the paper. Okay.
1 minus 3. No, whatever. There's something. Okay.
Okay, sorry about that. So I should check. Okay, so what it means now?
What do you take for gamma here?
Excuse me?
What do you take for gamma here?
Also, here for gamma we take 1 over r square. We take the largest possible gamma,
right?
Which is when r is. So when r is exactly this one, the base gamma is 1 over r square, and we keep the same one. Okay, which is known to be the best if you do a single pass. Okay, in those hard problems, so we keep the best possible gamma that we know for a single pass, and we keep on doing multiple passes. And gamma is 1 over r square, and probably a plus. Sorry about that. And so at the end, what we obtain is that, if you remember from my second slide or third slide, this was the optimal behavior. Okay, for that class of problem. So we show that SGD is achieving that optimal behavior if we have that mu less than 2r. And otherwise, we do an improved behavior because what we obtained before was n minus 2r, and we get n minus 2r over mu. So we do show an improvement, optimal sometimes and suboptimal in other times. Okay, so now if you go back to my plot over there, okay, so this is still incorrect. It should be plus. I'll check, and yeah, I'll check. Then, since we have this quantity mu has to be less than 2r, and if you take for subless spaces, mu is 1 over alpha, this defines a new region when 1 over alpha is 2r, above which we do optimal rate with multiple passes, and under which we do get a better rate, but it's not optimal. Okay, so here in this work, what we have done is essentially cut the hard problems in two, where you do optimal in one part and suboptimal in the other part. Now let's look at some basic simulations. So subole spaces like 1D. Why? Because you can, like in the earlier, we can choose R and alpha. And we need to check whether our optimal number of iterations is correct or not. So we say that if you do those many iterations with a plus, then you get that performance. We're going to check whether the best number of iterations is close to that. So we're going to do it for three sampling schemes. The one for which we have proof with replacement. The one which is often used in practice, where you do like without replacement, you select one data point, then select another one, and go on until you finish the data set, then do a reshuffle and start again, and pure cycling. So again, we have a proof for this one. We don't have a proof for this one. So I'm going to show 4 plots, and those 4 plots will be depending on values on alpha and R. This will be easy. This will be like at the border. This will be hard. Okay? And on all plots, I'm plotting now a number of observations. So this is every point here corresponds to a finite data set with a given n, and I'm doing multiple passes. Okay? And what I call T star is the number of iterations which had the smallest test error. So we run that entire curve, and we empirically consider the smallest one. So you see like data-driven selection of T star, and we plot T star. Okay, this is for every red dot corresponds to one run of like multipass LGD. And so for several n's, we get several values of T star, and on the what we plot as in the dotted blue line, this is like what we predict as a number of iterations. Okay, so this is the power which is incorrect. This is that power which we plot. Okay, and obviously this is the correct. Okay, we plot the correct one. Okay, so we plot the line and we cheat a bit. We fit a line of a given slope. So we fix the slope, but we put the intercept to stick with data. So first for super triple problem, okay, so what you observe is that the line of slope 1 does fit, but even nicer, the intercept is 1, okay, or is 0 in log scale, so meaning that really a single pass is enough. You don't need to do more than a single pass. In practice, you never need to do more than a single pass on that simple problem. When at the borderline cases, okay, when R is equal to my borderline case, then you get a line of slope 1. So the number of passes is a constant, okay, which is not 1, because you get 3 here and 3.5 over there, so it's a bit more than 1. And now if you go for harder problems, when R, which characterizes my difficulty of the problem, is less than the threshold, then you get like a line of slopes like 1.25, and that line has a slope which is more than 1, meaning that the number of passes, which is T over N, has to grow with data. So this is with sampling with replacement, so for which we do have some analysis. Again, our analysis does not predict such a line. Okay, we just say that if you do the correct number of passes, you get a good performance. This is empirically showing that the best possible number of passes. If you go without replacement, it's a bit more stable, but similar behavior. And if you go to cycling, same thing. It's also quite stable. Okay, it's even stable. We have no proof at the moment. All right, so let me. We also have like some data set. Okay, so NIST, for which indeed we try like to increase the number of samples, and this is similar. We obtain like the best number of passes does increase with the size of your sample. So this is true for NIST, but there are also many data sets for which the number of passes does not grow. Okay, so what we have is that from our analysis, we do have some hard problems for which you need to do multiple passes, but there are still simple ones for which a single pass is enough. All right, so let's conclude. So in this talk, we have tried to present results showing that for some problems you do need more than a single pass, and this is to the best of my knowledge, the first probable improvement of doing multipass LGD. Okay, so to be precise, there is like earlier work by Moritz Hart and colleague, and by Lynn and Rosasco, showing that if you do multiple passes, it's not too bad, in the sense that if you reduce the step size and then do multiple passes, then you recover the optimal rate of convergence. Okay, so they all, in particular the work of Lynn and Rosasco, they are all in that blue region, and they show that if you take a small step size, which is not optimal after a single pass, it will become optimal if you do multiple passes. What we consider is different. We take a region for which we know that a single pass is not optimal, given the proper step size, and we show that it becomes optimal after doing multiple passes. So extensions, so trying to go beyond sampling with replacement, because in practice people do stick cycling, okay? Then looking at mini batches, okay, clearly. So here it's a bit different because we should expect that if the mini batch size goes to n, things should start to change, okay? This is the effect of having a finite amount of data. Of course, beyond least squares, because this is all for least squares. And finally, belong, like trying to cover that region for which we don't know what's happening. And final results, it's mostly like an advertisement for another paper with the same authors, is trying to combine this with exponential convergence of testing errors. Okay, so here I focused on the testing loss in the regression setup, but if you go to classification, and if you're willing to make like margin assumptions, then you can get exponential convergence of the testing errors, and we would like, in fact, we studied to do that to combine those two together. Can you show that although the testing errors have almost converged, the training errors have converged? Can you still do you still need to optimize to get to better testing error? Thank you for your attention.
Sasha.
When you have these improved rates, doesn't this mean that you have different assumptions on safest file?
Sure.
The class is different.
The class is
How you
smaller.
improve the rate?
The class is smaller.
The class is smaller.
Yeah, okay, so, no, of course. So what we don't achieve, so clearly we divide the class in two, make a stronger assumption, which is this one, and then we get a better rate. Okay. Without it, it's not.
When you take this mu as small as possible,
We take the mu, yeah, of course.
then you get any rates because it's
No.
n to any power, n to the minus.
Sure, but that mu has to be true for your problem. And essentially, the mu is always bigger than 1 over alpha. You can, okay, at least for subway spaces, mu is 1 over alpha. And if you take it too small, it becomes vacuous. No, okay, so here in terms of like statistics, everything that we do is contained in the paper of Ingo. There is no novelty in terms of rates of convergence because those rates are also achieved by doing regularized risk minimization. Okay, so it's nothing new in terms of statistics, it's new in terms of LGD.
Can you say a little bit, so what happens in your analysis? How do you do that with t larger than n? And what happens when you do the improve? This is intuition, some idea.
Also, the intuition is that you have to change the proof techniques. Okay, so if you look at the proofs for t smaller than n, you rely a lot on independence. Okay, but as soon as you go to the n+1 data point, then everything is coupled, and you have to change proofs. So the proof by Rosasco and Villa, they really compare that recursion to the expectation over IU, which is a full gradient descent, and they stay close together, in fact, and you analyze when gradient descent is overfitting. So it's really leveraging a lot the analysis of empirical risk minimization is totally different. I wish we were able to really quantify the dependence between, like, so the next time you see the second time you see a point, okay, you have seen it before, but the dependence is a bit weak. So you would hope that it's almost like independent, but we have never been able to do something like that, make it concrete. That proof taking is totally different.
So the gradient descent is on infinite data, right? So you
No, this is on the untitled data.
Oh,
This is why it does overfit, because you get close to the optimum, so the bias term will go down, and then the fact that you're minimizing the empirical risk better and better will start to hit you, and you start to overfit. So if you do like gradient descent of the empirical risk, you will observe that performance. Okay, you first go down, then you overfit, and we just using that as a pilot estimate to get close to. But SGD will follow the same curve, but much faster in terms of complexity. And this is really the proof of Rotasco and Villa. And what we do, we just do it for average SGD with the using the optimal analysis of SGD.
Okay, let's take Francis once more.